First of all, don't say I'm a professor because I might get into some legal trouble. So, good morning, Tashi Delek. Thank you for having me. Thank the organizers for this. I've been having a great time, and especially Fernando for his patience. So today I'm going to be talking about a class of geometries that are referred to as flops of length 2, which we affectionately call the conifold 2.0 for various reasons. So this is work with Marco Fazzi and Roberto Valandro, who's in the audience. So the paper came out a couple weeks ago, and then I will connect that to an upcoming paper with Fazzi, Valandro, and Dave. So this will be discussed today in the talk by Valandro. So please regard this this seminar as a very lengthy appetizer for Roberto, who will answer all questions and puzzles in far more detail than I will. So the idea for this talk is it'll be, hopefully I won't be making any strong claims. What I want to do is present a class of geometries, singular geometries, that have been known for a while, but I believe have not received a lot of attention in the physics literature. And I will it'll be essentially an academic exercise. I will expose a set of techniques. Some were known about 15 years ago, but some have only been refined more recently by mathematicians, which has to do with the so-called non-commutative crescent resolutions of singular geometries on one hand, and how these can lead to what is known as a Quiver GIT treatment of singularities, where GIT stands for geometric invariant theory. So it's a way of dealing with a certain class of singular geometries where otherwise known techniques would fail. Okay. So this class of geometries, they're very interesting, so let me motivate why they're interesting. So first of all, they're like the conifold. And we all love the conifold. So what do I mean by they're like the conifold? So they're threefolds. They're non-compact threefolds. Sorry? Non-toric. That's why they're interesting. So they're like the conifold. They have an isolated singularity. The singularity admits a small resolution. And therefore a flop transition. So the exceptional locus of the resolution is a P1, and the P1 can be flopped. But they're non-toric. They're not orbifolds. And none of the extremely powerful techniques work. This family is called the threefold. They don't admit any of this. Now there are some techniques that were developed by Morrison and his former student Curto, that can handle actually resolving these things, and they involve something called the Grossman blowup. It's fairly complicated, but it works. But I think it obscures a lot of the interesting properties, like seeing the actual exceptional P1, following the Flock transition through continuously, seeing what happens. And so that's where these other techniques come in that are actually very explicit, but have never been applied for this class of geometries. Another reason they're interesting, so the particular class of these threefolds, you can create infinitely many of these threefolds. There's a construction by Dave and Kurt that gives you a universal family of these. So it's actually a sixfold, and then you can take any complex three-dimensional subspace of that passes through the singularity, and that gives you a threefold that has these properties already. So there's infinitely many of these, but the specific kind I look at happens to be embeddable in an elliptic vibration. So that's already interesting for considering F-theory on threefolds, so to 6 dimensions. So I don't think it's useful for the 60 SCFTs because the base is just C2, but it can still be interesting for F-theory proper if you embed it in something more compact, which you can't do. And finally, it's interesting, well, both from the F-theory perspective and the type 2, at least type 2A geometric engineering. Perspective, because it's the effective theory in 4D and the geometric engineering perspective it's S3D with one hyper, so kind of like a conifold, except that depending on where you are in the closed ring moduli space, you could either have a charge 1 hyper or you could have a charge 2 hyper. And the fact that it's charge 2 can be connected to other constructions in F-theory, as Roberto will explain in full, glorious detail. I'm sorry? Yes, it's a Calabi-Yau threefold. Right, so it's like the conifold story, except that you can have charge 2 states. Now you might say charge 2 is not so spectacular. We got grad students churning these things out all the way up to charge 4. But the point is that the principles that got you, sorry? That it's as far as people have gotten in F-theory. But there are questions of how high can you go, and notice that this is flops of length 2, and this 2 here, I would claim is connected to the charge 2, but it's actually possible to have flops all the way up to length 6. So there could be a hope that you could get things all the way up to charge 6. So that's one way of motivating why these things are interesting. This is what is question, right? That's what people want to know. Several talks, in fact, an entire workshop was dedicated to this a month ago. Okay, so all right, let me start. Let's see. Right. So let me give you an idea of what do I mean by this flop of length 2. So I should say, so the geometries that I will present, they're known as Laufer's examples. As far as I know, they've only made it into physics in a paper by Comron, Cachasso, and Katz 15 years ago. They handle that in a different way. So I think that what we're about to do is more comprehensive and can encompass a lot more. It will not depend on the way that the geometry was constructed so severely. So first, let me define this notion of length. So this is something that it's an invariant of flops that was invented by Collar. And so the first thing I'll tell you about the length is that the conifold that you know has length 1. Okay? Now, that doesn't tell you much, but it already tells you why we like to think of these geometries as the conifold 2.0. They're kind of like the prototype of the next version of this. So what's the idea? Well, let me give you an example that you might know. Take the ADE surface singularities, right? And take, for instance, something like a DN singularity. Now, you might know that if you blow up, a non-compact K3, for instance, with a DN type, you know that these P1s in the resolution actually come with multiplicities. And the multiplicities are the Dynkin labels of the adjoint representation. So the point is that the inverse image of the singular point is something like, it's a sum over curves, but the curves come with multiplicities, okay? And so this is exactly what is meant by the length. So in the length, if you have a length L flop, that means that the inverse image of the singular point is going to be one curve, a P1, with a given multiplicity. Okay. In fact, the way that these things, the length 2 things, are constructed is actually by looking at the deformation theory of the D4 singularities and taking a family of these in such a way that you only keep this node. So it automatically gives you a length 2 thing. And the other constructions for high length rely on the other Dynkin diagrams. And that's how you get this hypothetical upper bound 6, because that's what the diagram of E8 would give you. Okay. All right. So that gives you an idea of what it means by the length. So I think it can be defined a bit more precisely by saying that you take the pullback of the skyscraper sheaf over the singular point, and that's going to be something like the structure sheaf of a curve, but that essentially means the same thing. Okay. Right. So. So let me show you, without further ado, what the geometry looks like. So just look at this thing here. You can neglect the lower half of the lower part of the blackboard. So it's a hypersurface in C4. It's purely accidentally, it already has a nice Weierstrass form. But if you try to treat it like the conifold, you will not succeed. You cannot write this in the form AB equals CD that you would need for a small resolution. So you need something else for that. So this was, so the way it was created by Laufer was by starting with requiring that the normal bundle of the exceptional curve be of a specific kind, and then he came up with this. But it can be obtained by this so-called universal family of threefolds, just by making a particular slice of it. Okay. So let me just write it up here again. Maybe I'll do it over there. Yeah, this seems to be the simplest example. I wish there were something simpler. So I should say a few things about it. The conifold that you know, the exceptional P1 has as its normal bundle O minus 1 plus O minus 1. And in fact, not only the conifold, but the so-called Reed's pagoda. Reed's pagoda has normal bundle O plus O minus 2. This is another infinite family of floppable threefolds. Now, this example, are known as Laufer's examples. And by the way, n is any integer you want. So this is a discrete series of examples. They have something very strange. The normal bundle is actually not strictly negative. Okay. So you might worry about the rigidity of the exceptional P1, but it turns out that this is obstructed. The P1 has higher obstructions that can be encompassed in a superpotential. But the fact that there's something positive here, I would claim makes new things possible that were not possible here. Namely, you can have bound states. If you put several branes on the sphere, they could form a bound state, because the strings that go from one to the other have to be sections of the normal bundle tensor with something, and now sections of the normal bundle actually exist. Right. Sorry? No, okay, that's a good question. Yeah, okay, you could say, well, okay, so the pagoda is like a borderline, but then this will be impeded by D terms in the end. You will not be able to switch it on. You do need something strictly positive. So I will not do the calculation, but so what can I say about this? So first of all, as you can see from its definition, this hypersurface cannot be written as a binomial, so it's not toric. And like I said, it's not an orbifold, so none of the usual methods work. And that's why we need to tackle this with these so-called non-commutative Crepert resolutions. So let me explain what these are. Where did I put it? So NCCRs. So these were invented, or at least defined by Joris van den Berg. Although some mathematicians also give credit to and Lee around the same time. And for the specific, sorry? So this is around 2000, 2001-ish. But at least in one review written by mathematician Leszki, he actually credits them first, whatever. But mathematicians will say that he put it down on paper, he actually defined it, but somehow everybody knew already, it was already in the air. In the particular examples that I will be studying, I will rely heavily on a paper by Aspinwall and Morrison. Okay. So first, I need to define what is a singularity. Okay. Now, of course, in this audience, I don't need to define it. We all know, especially for hypersurface, it's very easy. If the gradient has a solution, it has solution points that are also solutions of the actual hypersurface, then it's singular. Fine, that's one definition, but that's actually not the definition that these people care about, or at least it's not the only one. They have a different way of looking at it, and since they are fellow sentient beings, we should take an interest in what makes them tick. So, what is their definition? Well, first I'll give it, and then I'll explain what it is. They would say that there's something called a global dimension, and a space is singular, the global is infinite. Okay, that's it. Thank you very much. So now let me work this out in an example. Let me do a little bit of basic homological algebra, and we'll see what a symptom of a singularity is. So first let's start with a smooth space, right? So let's take this ring, polynomials in x and y, okay? And let's say I want to look at the ideal x comma y. Now this is a module over that ring. If you don't know what a module is, it doesn't matter. It's essentially like a vector space, except that the coefficients are over a ring instead of over a field. Okay. Now, what does this ideal mean? It's any polynomial that can be written like this, right? Where P and Q are polynomials. So you might ask, well, how can I parameterize all possible elements of the ideal? And the first answer you give me is, duh, you just give me a pair, P and Q, and I'll just dot it into x, y. That should do the trick, right? Now what's wrong with that picture? Right? I could just make the stupid choice of giving you, as P and Q, I could give you minus yx, and then I'm not giving you anything. So I should somehow mod out by this. So let's just do it. Now let's translate this into technical language. So the first approximation, the first answer, let's call this guy R thing. Okay. The first answer was, right, you take any element like this, and you map it to xp plus yq. But we see that there's a kernel to that, and the kernel being this particular choice. Okay? And after that, maybe I should do the transpose of this, otherwise I see conventions. Now you could ask, does this have a kernel? No, it doesn't have a kernel. So the sequence terminates. So this is what you would call, in this case, a free resolution of this module. And you see that it terminates after 2 steps. So it's finite. Okay. Now let's try this again. I should move around a bit. Let's try this again for the conifold. Let's say I live here. So my ring is this, and I would like a resolution. I would like to look at this particular ideal. Okay, so now you might you would once again say, well, start with this, and now, of course, that lesson carries over. You'll say, well, for sure, this generates a kernel. So I should have an R here. And now you might think you're done, right? But this is not the only possible kernel, because now you could also give me P and Q that are equal to y minus w. If you dot that into this thing, that's also 0 by virtue of the hypersurface equation. So now I should put that in here, like that. And now my resolution is a bit different. Because now what you'll realize is that even here, and now because you have a matrix, there's a possibility of a kernel. And indeed, there is a kernel. And that's the following matrix. What do you do now? What you will find is that the problem persists. And you never end. And this, so of course, even in the regular case, I could have picked, if I want, I can pick an incredibly stupid way of resolving this so that this is also semi-infinite. But that's what you would call not the minimal resolution for this. You can trivially extend this. The point is you have to always try to be honest and get the minimal one. And in this case, it's not due to a stupid choice. This is as short as it gets. So this is what they call having infinite global dimension. So meaning you have to check for all possible modules, and for each one, get the smallest possible resolution. So this has a number of steps. This is a number. And look for the biggest number that you can find in the space of all modules. That's what they call the global dimension of that ring. And it is singular if and only if the global dimension is infinite. So that's what the people of NCCRs call a singularity. Okay? So are there any questions about this? Yes. Yes, indeed. Yeah. So this is the matrix factorization of the conifold, and I will talk about how the matrix factorizations actually come into the game to solve this issue. So I think if the ring is Cohen-Macaulay, any resolution that is not finite, it might start out differently, but it'll eventually stabilize to this thing. That is Eisenbud's result. Okay, so now I've defined what a singularity is from this homological point of view in pretty down-to-earth terms, I think. I hope it's down to earth. So now I will explain what the remedy is. So again, this was formalized by Van den Berg. But if you want to actually learn these things, I recommend a very nice set of lecture notes by this guy. So this is in IPA. I think it would be spelled just so you know how to pronounce it, Weems, which you might not expect from the spelling. So he has a nice set of lectures from 2012, I believe, where he explains these things. So what's the idea to deal with this problem? Well, the idea is to replace this bad ring with some other ring. Let's call it A. And we will require some things. So first, it has to look like R in some way. And what does that mean? So this ring will be non-commutative. And one thing that you'll require is that the center, the abelian part, isomorphic to the original one. So this is kind of the criterion that it actually blow down to the singular thing in some homological way. The second one is you want some notion of crepancy. And this one is tricky. It's a technical definition. You impose that this is Cohen-Macaulay over R. I will not try to define it, first of all, because I never fully got the definition. But it has to do with the depth of this thing as a modulo over R. It doesn't matter. There's a well-defined procedure for testing whether it is Cohen-Macaulay. And finally, we want the global dimension to be finite. And this is the criterion that tells you you've actually smoothed out the thing, as opposed to maybe having done a partial resolution or something like that. And in fact, if it is finite, it'll turn out that it'll have already the dimension of the original thing. So you won't have increased or lost dimensions. So it's a reassuring consequence of some theorems. Okay. So. Okay, so how is this done in practice? So first is you have to find a module M over R that is itself satisfies the property of being maximal Cohen-Macaulay. I'll explain what this means in down-to-earth terms in 1 second. The second thing you do is you build a ring out of this, an algebra actually. Let's call it A1. And you build it as a ring of endomorphisms of the R, the original singular ring, plus this guy, this thing here. You compute this, and then you see if you test to see if A is an NCCR. So if the answer is yes, then you're done. If it's no, then you start again. You find another candidate module, and eventually you just start adding modules like this. And at some point, the procedure terminates. At some point, so let's call this a K. At some point, it terminates, and then you have the thing that has finite global dimension. Okay. Otherwise, anything before that will be something that's not completely smooth, and it'll still have infinite global dimension. Now, the good thing is, for our purposes, one module will always do. Okay, great. And now there's a theorem that is, of course, maybe the most relevant for us, which is for threefolds, is that R, the singular thing, admits an NCCR if and only if the X, let's say the singular space that had the ring R, admits a small resolution. So an actual geometric commutative small resolution. So that's already one reason why these NCCRs are useful. This is for dimensions less than or equal to 3. Unfortunately, for F-theorists at dimension 4, it's no longer true. Neither implication is correct. The most famous example being C4 mod Z2. It admits an NCCR, but does not admit a Krapin resolution. Okay, so how do we do this procedure? Step 1. Sorry? The fact that it has no symplectic one, well, I guess, if it had a Kähler resolution, that would be symplectic, right? The Kähler is symplectic, right? No? Ah, okay, well, but then you could also have a non-Krapin resolution altogether, right? If you don't care about supersymmetry. Yeah. Okay, so let's do step 1. Let me explain what step 1 means. So what is an MCM module? So for hypersurfaces, it's actually very simple. It's essentially like this. It's anything that can be described with a matrix factorization of a hypersurface. So let me explain. So if you have a hypersurface, meaning something given by p equals 0, matrix factorization of P, it's a pair of matrices, square matrices of any size, so n by n, such that their product in either direction is the identity times P. Okay? Now, so this concept was invented by Asimov in 1980, and it made its appearance into physics around 2003 or so. Many people worked on this from the Landau-Ginzburg point of view. One of the main people who worked on it is sitting in the back, Hans. So they already have, they're already interesting even from the closed string point of view, but I will apply them in the from the D-branes point of view. So what is an MCM module? It's anything that can be written as the co-kernel, something like this, so of a matrix like that. So if you have a matrix factorization, like I gave, then this defines for you a map in fact, you have this semi-infinite complex that is periodic. It alternates. And in fact, it's like Hans noted, but I already erased it. That's what we already saw for the conifold. We have this sequence of 2x2 matrices. And then the co-kernel here will be a module, the co-kernel of the last map. And that module will have certain properties that are called maximal Cohen-Macaulay, of which the definition is very involved. But for the hypersurface case, that's all we need to know. Okay. Now, notice that the pair is ordered. So if I have this matrix factorization, swapping psi and phi gives an inequivalent one, and it gives an inequivalent module. I should specify. Right. Okay. So for the conifold, let me write this again. In the case of the conifold, my matrix factorizations are x, y, z, w, comma, y, x minus z minus w. So one ordered pair will give me a module. The other one will give me a different module. And for that case, it turns out that the non-commutative Krepin resolution only requires me to choose one of the two. And this is the NCCR for the conifold. Now, let's see a little bit more what this looks like. So endomorphisms means maps of this to itself. So it can actually be represented as a quiver with arrows, right? So you can decompose this into Hams of R into R, M into M, R into M, M into R, right? So what do arrows mean in this language? For instance, what is a morphism of R into M? Well, you write R up here, and you substitute M by its resolution down here. So in the case of the conifold, and here I have my matrix, and a morphism from the upper one to the lower one is a sequence of vertical arrows. So in this case, it's just one arrow here, alpha. But I do have to mod out by what are known as homotopies. So I'm defining alpha as being equivalent to alpha plus psi dot delta. Okay? And so in this case, it's very easy. There are two, there's just these two maps that I have to take into account. So just literally these two by one matrices. And I'm done. Now, what does the other direction look like? Well, in the other direction, so beta would be something like that. Like that. So now I don't have to worry about these homotopies, but I do have to make sure that this composition, that this composes to 0. Because you see here I have a 0 that I'm not drawing, and all squares have to be commutative. And this path here is 0, so this had better be 0. So I have to set that to 0, and it turns out that here all I need are the rows. Sorry, the rows of the partner matrix will do. Because you see, I already have the fact that it's a matrix factorization. So phi dot psi equals psi dot phi. It's equal to 0 if I'm restricting to the conifold, to the hypersurface. Right. So the rows of psi provide me with a natural set of vectors that will kill this thing. Okay? So, so I can already start to draw a quiver with this, and now you'll start to feel like you're in familiar territory, at least for a while. So I have two alphas going this way, two alphas going that way. At this point, you should feel a sigh of relief. Ah, okay, not so crazy after all. Now you might ask, what about relations? I know that, right, there should be a Klebanov-Witten superpotential somewhere in here. And so we can try it. So let's do beta 1, alpha 1, beta 2. Let's try and compute that. And now is when I will wish I had stuck to my own convention. So if you calculate this, at least in some set of conventions, you will get a row that looks like this, for instance. And now let's try this one where I swap the betas. And there I get something like this. Now, are these two equal? These two vectors, well, the first components are equal. The second components are equal by virtue of the conifold relation. So I can set these equal to each other, and you can test, you get all the relations, and so you can reproduce the Klebanov-Witten superpotential like that. Okay. All right. So now that I've done the conifold in detail, I can just give you the results directly for Laufer's example. So, first of all, are there any questions about this so far? No. All right. So, Laufer's example, it's a hypersurface. It also admits matrix factorizations, but now they're not 2 by 2. The only ones are actually the minimal, irreducible, optical equivalences are 4 by 4 matrices. And of course, I could also swap these two matrices. And here it turns out that once again, to get a non-commutative Krepin resolution, all I need is this. So just take this one. And if I now look at relations, so if I draw this again as a quiver with a path algebra, I will get a quiver like this. I apologize for the potential phallic interpretation of that quiver. I'll just say that it's no worse than Luca Martucci's warped Calabi-Yau of Monday. So anyway, so you get this quiver, and you get a superpotential like so. That gives you all the relations for that quiver. Okay? And this is the NCCR for this guy. All right. Now, you might say, okay, great, that's I'm really happy for you, Andres. But what do you do with this thing? What if I want to understand the geometry? So, by the way, this stuff was done already in the paper by Morrison and Aspinwall. And it kind of ends here, their analysis. And then there's a lot of questions. First of all, can we do a bit of geometry? Can we understand? So if Van den Berg tells you that the existence of this NCCR implies the existence of an actual small resolution, how could we see it? Also, if it's supposed to be a flop of length 2, where's the flop in this? You see, the conifold quiver, we had a nice, there's a nice Z2 symmetry, so you might think, well, maybe the flop is something that switches left node and right node. Kind of makes sense. And here you have no symmetry that flops, that switches the nodes around. The only thing that you have is really that you could just swap these two guys. And you might think that might have something to do with the flop, but it's not very satisfactory. Also, maybe you don't want to just see the exceptional P1. Maybe you also want to see the non-compact divisor that cuts that exceptional P1, because ultimately that's the divisor that will give rise to the U1 gauge symmetry if you were to compactify this thing, and that will give charge to the membrane wrapping that P1. So that's what we studied in our paper, is how to get some geometry out of this. And for this, we used what is known as the Quiver GIT. Yes? I just what? I'm sorry? Yes. Sure. So, yes, there are singularities that don't admit NCCR. No, if they don't admit an NCCR, they don't admit a small resolution, like geometrically. Ah, okay. Mm-hmm. Mm-hmm. Okay, so you're saying it physically should still exist even if it doesn't admit. Yeah. Can you have this? Well, so can you have Gornstein? I don't know enough about, well, maybe Timo or people. So for threefolds that are Gornstein, can you have the situation that there's no Krepin resolution? Is Timo here? Is this thing on? Sorry? Isolated singularity that doesn't admit anything, yeah. And it's going, okay, yeah. I don't know the status of these. I mean, of course you should think that you should be able to probe it with a D3 and... Sorry? There's always something possible. Okay. Maybe that's the answer. Yes? Yeah, so, okay, so in this case, the quiver will look the same. There are some situations where the quiver looks different. They're all, yeah, they're like the Seiberg duals. They're all derived equivalent as rings. Well, if you don't take the minimal ones, no. Well, then you should. Then you probably don't get an CCR. For instance, you could make it simpler. You could take m plus the syzygy m, so the one where I swap these two. You could take r plus m tilde, and even for the conifold. And what you find, so if you do this overkill thing, what you find is that it's no longer an NCCR. So it's kind of like doing a large resolution. It's like doing the blow up of the conifold in the most brutal possible way, and then you don't. Yeah, so here I have to make a choice out of two possibilities. Yeah. But that in itself, so it might be linked to the flop transition, but in my case it will not be actually how we think of the flop transition. Yes?
Maybe I'll just basic. Can you just explain the geometric and physical interpretation of the quiver?
Yeah, I'm coming to that. Yeah.
Okay.
Sure.
So far it's kind of
Yeah. So now we'll see. I mean, you might suspect. We'll understand how this can be thought of as a quiver of a probe brain, right? That you put on this. And so the way to do that is to look at quiver representations. Okay. So. The direct quiver. So the derived category of modules over this ring is equivalent to the bounded derived category coherent sheaves of the resolved space. Meaning that you can look at all branes on the singular space as modules over this thing, meaning you just need to look at quiver representations to get, you need the derived category of quiver representations to get all possible branes on the singular space, but they can all be linked via the resolution to some actual sheaf or object like that. Okay, so now we need quiver representations to understand the singularity. Now that we have a way of extracting the quiver, which bypasses the need for something toric or orbifold-like, now we can move on to looking at moduli spaces of quiver representations, which is what physicists do when they probe singularities with branes. Yes, this one. I'm sorry, yes. So okay, fine. So this I'm making, for the purposes of this talk, I'm making the choice n equals 1, but the quiver has been worked out for all n's. It's in there. Yeah. Okay, so quiver representations. So what's a quiver representation? So in this case, it means that at each node, put a vector space C to the D left and C to the D right. And so all the arrows now become appropriate matrices. And now I will explain what the D has to be. So D has to be a DL by dr matrix, and so on and so forth, such that it works out. So A and B are square matrices, so they're dr by dr matrices, et cetera, et cetera. Okay. Now, there's a theorem. So I think it belongs to Weems. It tells you that that what you have to look at, so the dimension vector has to actually be the ranks of the modules. So in this case, rank of R and rank of M, seen as R modules. And if you make that choice for dimension vector, then you will get an actual small resolution for this thing. So a geometric resolution. Okay. So for the conifold case, let's look at it again. For the conifold, I had my ring R, so that would be considered rank 1. And I had this guy that was given by a 2 by 2 matrix, the co-kernel of a 2 by 2, but it's a 2 by 2 that always has rank 1 on the rank, at least away from the singularity, but on the conifold, it always had rank 1. because its determinant was 0. So the co-kernel with rank 1, 2 by 2 has rank 1. So that would have been the representation that you needed for the conifold. Now here I have a 4 by 4, but it actually, you can work out that almost everywhere on the singular space it has rank 2. So that means we need to look at the 1, 2 representation. In other words, a D3 on Laufer's example is given by the following quiver gauge theory. You're going to have U1 cross U2 with the arrows that I just gave you and the superpotential there. So now the point is that we recover the resolved threefold as the moduli space of this quiver representation. And so what is that? So that's given by, so you take this space generated by A, B, C, and D. You have to impose some D-flatness, which is going to do the equivalent of removing the origin before you construct a CPN, for instance. And now you have to mod out by the complexified, so you either remove some bad points or you impose D terms. If you just remove bad points, then you have to mod out by the complexified gauge group, which is C star by GL2C. Okay, so it's U1 cross U2, where there's an overall C star that drops out because no one is charged under it, blah, 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 right? Okay. Okay, and so now you can also see why it had no hope of being toric. It's the fact that, sorry? And, yes, sorry, yeah, modular relations, of course. Okay, so let's see, let's try to see how we can extract a P1 out of this, okay? So first I should mention that, so the D term constraints, the D terms look like this, right? So at each node, at the ith node, you put a parameter, an Fi term, and then you do all arrows. You sum over all arrows that go into the ith node, and you have the field times its dagger minus all arrows that go away from that node, and you have the dagger minus itself, which I'll write in this case. And also, we make the choice that the theta vector has to be it has to be such that when you dot it with the dimension vector, it's 0. So in our case, that means we want some parameter psi. And so on the left, we're going to put minus 2 psi on the right, plus psi. Psi is a real parameter. It can be positive or negative. That's how we'll see the flop transition. So just like for the conifold. And so here the D-term relations are Okay. So now we want to look for the exceptional curve. So how can we look for this curve? So I use a tip that I got from Reinecke, which is to set all gauge invariants